Okay, what we would have done new in class today was talk about vectors and scalars. So I won't do everything we would do in class today. I'll leave some for tomorrow, but I just want to get you started. For those of you that had science in French, I think you probably talked about vectors in grade 10. For some reason, the French curriculum does, but the English curriculum doesn't. So some of you have probably never heard of vectors and scalars, or at least not in the way we talk about them in physics. Some of you probably heard of vectors before, because Vectors is a brand of hockey sticks. It's a cereal. It's granola bars. None of those are what we use when in physics. Okay? A vector is simply any quantity that needs both a number with a unit and a direction to describe it. So a vector would be like if I was pushing on a box with a force of, let's say, 40 newtons, and I was pushing to the right, then that's a vector, right? Because it needs a direction. Like if I have a box on the floor and I ask two of you to push with the force of 40 newtons so that you can move it down the hall, and I don't tell you the difference about direction, the two of you might push with the 40 newtons, but one might push with the force of 40 newtons right, and the other push with the force of 40 newtons left, and you won't be going anywhere in a big hurry. Okay, so vectors are things that need both a size, with their unit, of course, and a direction. So things like velocity are vectors. Velocity is like you're going 80 kilometers per hour east, or acceleration. Acceleration is really important to have the direction on there, right? If someone says to you, accelerate, accelerate, that could mean speed up or slow down. They might be wanting you to step on the brakes. If they don't indicate that, you might be hidden into an accident. So those are vectors. Scalars, on the other hand, are a lot easier. Scalars are just things that just have a magnitude. For example, time, 30 seconds is a scalar. You would never say 30 seconds east. How long did it take you to come to school today? 10 minutes north. No, we don't say that. Temperature is also a scalar. For example, we might say minus 10 degrees Celsius. We don't say minus 10 degrees Celsius to the right, right? No, there's no need to put a direction on a scalar. It doesn't need it. It's completely described with just its size, or you'll often hear us say with the magnitude. Magnitude just means size. Okay, so what we need to look at, though, is vectors, because they're the special ones. And from this point on, when you hear the word vector, I want you to think of an arrow, okay? Because a vector is really symbolized by an arrow, where the length of the shaft is how big the arrow is, and the direction that the vector is pointing in is usually shown by the direction the arrow is pointing. So this might be something like 50 meters east. Well, because another, okay? Whereas this might be 25 meters north, right? So this one is about half the length of the 51, and it's pointing in the opposite, in a perpendicular direction. Okay, so the length of the shaft tells us about the magnitude of the vector. The direction that the arrowhead is pointing in tells us about the direction that the vector is going. Now, the thing about vectors is we have to be careful when we add them, because we have to take into account their direction. Up here, I could have said to you, what is the total force acting on this box if they're both pushing with 40 newtons? Well, if we ignored the direction, one might say 80 newtons, and one might think that it was going down the hallway the way we wanted it to. But if you take into consideration the directions, then hopefully you can see the total force on this box is actually 0, and it's not going to be going anywhere quickly. So when we add vectors or subtract vectors, we need to pay attention to their directions. And so because of that, we have what are called 4 cases for adding vectors. And I will give you a sheet of notes on these tomorrow. So right now you can watch them. If you want to take your own notes, you can, but just know that I will give you a whole sheet on them tomorrow, okay? Case number one is really easy. Case one is when the vectors are going in the same direction. Because when the vectors are going in the same direction, and maybe I'll use force. So let's say we have a 30 Newton force going east, and we have a 40 Newton force going east. What will be the total force acting on this box? Well, hopefully you can figure it out because it's pretty much borderline common sense. If they're going in the same direction, the rule is add them and keep the direction. Now there's a slight other rule actually. It says that in order to add vectors, you always have to line them up what's called head to tail. You have to put the tail of the second one on the head of the first one, because then the resulting vector, and I'm just going to get a different color, the resulting vector, what you get when you add them up, will always start where the first one started, and it will end where the last one ended. Ooh, my red pen is dying. That's not good. Let me find a different one. Okay, so starts where the first one started, ends where the last one ended, and it will be 70 newtons north. It doesn't have much more life either. This vector that you get as a result of adding two or more vectors together, it has this really high-class name. It's called the resultant. Told you this was borderline common sense. So whenever you hear the word resultant, it just means the vector that you get as a result of adding the other ones. When two vectors are going in the same direction, we say they're at an angle of 0 degrees. So that's case one. Case two is when two vectors are going in opposite direction. And again, this is going to be borderline common sense. Okay, this is back up here to this example. What would you do to get the resulting vector if they're going in opposite directions? So if I have 30 newtons going east, and I have 40 newtons this time going west, hopefully you'll be able to predict that the resultant will be 10 newtons west. So the rule is subtract them and keep the direction of the larger. If we were to draw it, we would have to line them up head to tail. So here would be my 30 newtons east. Here would be my 40 newtons west. And the resultant, like we said before, will always start where the first one starts and end where the last one ends. So it would be right here. It would be 10 newtons, and it would be to the west. Okay? The angle between them this time, opposite directions, 180 degrees. All right, case three. Case three is if they're at right angles to each other. So if they're at right angles to each other, so now here's my 30 newtons going east, but this time my 40 newtons is going north. Okay, right angles, 90 degrees. So what we would have to do for this one is first move them head to tail. I would have to move my 40 newtons over here, and I am going to run out of video here in a minute. So I will start tomorrow with this. So if you've watched at least this much, I'll keep going till the video ends, but if you've watched at least this much, we have a good start on tomorrow. So 40 newtons going east, north, my resultant would be right here. What would I do to get it? Well, hopefully you notice this is a right angle triangle. I could do Pythagorean theorem, square 30, square 40, take the square root. I'm going to get 50 newtons. But I also need to solve for the angle. So this is where our trig stuff comes in. So you would do inverse tan. So tan theta will equal 40 newtons over 30 newtons.